The sort of faults we get with thermocouples are the junction tends to fall apart. If the junction starts coming apart, then we don't get a good junction. We get decalibration occurring. If the metal starts to oxidize, we can get decalibration occurring because the metal is effectively changing into a different substance. If the metal starts to change because it's overheated, when you heat metal, you can radically change its characteristics. That's why we heat metal and then we work it. If you're making a sword or something, you heat the metal, you beat it, and then you quench it by sticking it in oil or cold water. And sudden heating or cooling changes the nature of the metal. Shunt impedance can also be a problem. What the shunt impedance is a breakdown in the resistance between the leads. That can cause a problem. Another big problem we have is if we consider the construction of a thermocouple. A thermocouple is, you get generally a probe, and then you have the two metals coming in. You get one metal coming in, forming a joint, and then you get another metal coming in, forming a joint. And generally speaking, the probe is full of that horrible powdery stuff that you get inside MIMS cable. You know the stuff I mean? That white powdery stuff. Now, that should give you a lovely high resistance between the two. But if water, just get that, if water starts getting in there, then now we have two metals, we have voltage, and we have liquid. We start getting galvanic action occurring. It all starts behaving just like a battery, and we're going to start getting false readings. We're also going to start, because water is a conductor, then we're going to start to get differences in our shunt impedances. So they're the sort of things that can give us errors. Water getting into the probe. Now another thing that's interesting, now I'll do is I'll put another sheet up, is if you get your standard thermocouple, there's my one thing, your standard, there's a junction going down, there's another junction. If you get your standard thermocouple and reverse the reaction, so if I put a lot of volts across here, say 300 volts DC across here, then the reaction reverses. A thermocouple creates volts, but when I shove volts into a thermocouple, one end gets hot and the other junction gets cold. It's a bit like an electrical fridge. And that is called the Peltier effect. It's the fact that a thermocouple, the reaction, the thing that occurs in a thermocouple is reversible. If instead of creating volts we shove volts into it, one bit gets hot, the other bit gets cold. It's not a very practical method of cooling. It uses a lot of power. You don't have to use two metals when you're building thermocouples. You can actually use P and N type silicon. And if you use P and N type silicon, you can make these flat sheets of silicon. They've normally got metal on either side, or ceramic on either side. And when you put high voltage across them, one of the sheets gets hot and one of the sheets gets cold. Now you can buy little fridges in the shops that are little fridges, and you plug them into your car electric heat, your car cigarette lighter, and you can put a beer in them, and it will cool down one can of beer. They're not very practical. They do pull a lot of power, and they will flatten your battery. But they're using a thing called the Peltier effect. Peltier effect coolers are used if we need to cool down critical bits of electronic. So for instance, if you're using lead sulfide lie detectors like to run about 4 degrees C. So we'd use Peltier effect coolers to cool them down. The important thing to remember is it takes a lot of voltage to do this. So you're talking about 300 volts. If you're using Peltier effect coolers anywhere, there's going to be 300 volts somewhere. There's not enough current so that it will kill you, but there's certainly enough so that it gives you a nasty bite. Another type of temperature measuring system uses infrared pyrometry. Pyrometry just means measuring of temperature. So infrared, we're using the infrared being emitted by an object. The hotter you make an object, the more infrared it gives out. If you get an element from the inside of a globe, if you make that hot, it glows. It gives out infrared energy. So by measuring the amount of infrared coming off an object, we should know what the temperature of that object is. There's only one slight problem with this. And the slight problem with this is not all objects are equal at their ability to absorb and transmit infrared. So, looking at this, maybe I'll just put a sheet up out there. If I've got a box, oops, that's not what I wanted to do. All objects. I'm going to have to just shade all that in like that. If I've got a white box and I've got a black box and I put a hot object inside both of those boxes, the white box will transmit the white box will transmit heat. Heat will come out of the white box. But the black box is much better at transmitting heat. So the black box will transmit even more heat. Because black is good at transmitting heat. Basically the rule goes, if it's good at absorbing, it's good at transmitting. So white objects are not very good at absorbing, they're not very good at transmitting. Black objects are very good at absorbing and very good at transmitting. The problem I have is if I have an infrared temperature sensor, oh, you can't really see that, can you? If I have some kind of infrared temperature sensor, and I'll stick it to about there, and I've got the same infrared temperature sensor in both cases, the top infrared temperature sensor will tell me that the temperature is perhaps 30 degrees C. The bottom infrared temperature sensor might tell me that the temperature is 60 degrees C. Now in actual fact, both objects are the same temperature. So we're not actually measuring the temperature, we're measuring the object's ability to transmit temperature. An object's ability to transmit temperature is called its emissivity. It's emissivity, and that's the symbol for emissivity. Now, emissivity of an object is a number that goes from 0 to 1. An object which is the perfect object, an object which is perfect at absorbing and transmitting heat, is called the ideal black body. The ideal black body has an emissivity of 1. The nearest thing we have to an ideal black body is those American stealth fighter planes, which are like black on black. So the ideal black body is a perfect absorber and a perfect emitter. Everything else is not a perfect emitter. Black surfaces have emissivities of around about 0.8 or 0.95. White surfaces have emissivities of around about 2 or 3. A shiny metal surface will have an emissivity as low as 0.1. If you try and use an infrared temperature sensor to measure a shiny object, you will get a ridiculous reading. It will be out by lots and lots. If the object is actually at about 80 degrees C, the infrared temperature sensor will read maybe 20 or 30. So this emissivity is a measure of how good an object is at reading temperature. Oh, sorry, emitting or absorbing or emitting heat. There's two types of infrared temperature sensor. There's the type that have a fixed emissivity, and it's usually set to 0.95. They're the cheap ones. Now, when you're measuring temperature with a cheap infrared temperature sensor with a fixed emissivity, you're not actually measuring temperature. What you're actually measuring is the color of the object. You're actually measuring the color of it. You're actually measuring whether it has a matte or a shiny surface, a gloss surface, because matte surfaces are better at absorbing and emitting infrared. So you're just measuring the color of the object. The more expensive infrared temperature sensors, you can vary the emissivity, and they will give you a correct temperature reading. Now what you're supposed to do is, if I have an object, say a switchboard, and I have a temperature sensor, what you're supposed to do is, you're supposed to plug a thermocouple, TC, you're supposed to plug a thermocouple into your infrared temperature sensor. There'll be a socket on it so you can plug a thermocouple in. You then touch the thermocouple to the switchboard. Now, and then you press the calibrate button. Because the thermocouple will read accurately, the thermocouple will come back and say, yeah, the switchboard is at, say, 30 degrees C. What the temperature sensor then does is it calibrates a new emissivity. So it calibrates an emissivity of, say, it's green, so 0.6. And then you can use the infrared to measure the temperature. And as long as you're reading this green object, you will get a correct temperature. It will come back and say it's 30 degrees C. Or if it warms up, it will say it's 40 degrees C. And you're now calibrated for reading this green switchboard. When you go to read the next switchboard, if the next switchboard is, say, yellow, then you have to recalibrate the infrared temperature sensor again. You have to plug the thermocouple in, you have to touch the thermocouple to the switchboard, press the calibrate button, it comes back with a new emissivity number of maybe 0.3. And then your temperature sensor is now calibrated for reading yellow switchboards. And you'll be able to use it for reading yellow switchboards. If you go back to the green switchboards, you've got to recalibrate it again. So you can't just use an infrared temperature sensor to walk around and measure lots and lots of different things. It doesn't work. You're not measuring the temperature, you're measuring the color, and you're measuring the surface qualities, whether it's matte or gloss. Having said that, why would we use, what applications would we use an infrared temperature sensor for? Now you say hotspots. Yeah, I think somewhere where it's unsafe to access. The nice thing about an infrared temperature sensor is it's non-contacting. So you don't actually have to go in. If you're measuring the temperature in, say, a crucible full of molten steel, all you have to do is point the thing at it. You don't have to go into the crucible. If you're measuring a flame, to make sure that there's a flame present, sort of places we do this, if you've... oh, that's a terrible colour, is it? If you've got a flame tower, a flare tower on an oil rig, you've got this dirty great big flame, and it's really important to make sure that that flame doesn't go out. So what we can do is we can have an infrared temperature sensor looking at that flame. In fact, we use infrared temperature sensors for flame detectors in boilers as well, to make sure that the flame is lit. So, they're good because they're non-contacting. They're good if you calibrate them for the one application you're going to look at. But when you move from one thing to another, they need to be recalibrated. Another thing to bear in mind is, if you're measuring something, then the sensor sees in a cone. So if you're measuring a switchboard, and that switchboard is 3 meters away from you, say, here's the switchboard. If you're measuring that switchboard and you're 3 meters away, you're not just measuring the switchboard, you're measuring the switchboard and all of the wall around it. Whereas if you're only 1 meter away from that switchboard, you're measuring pretty well the switchboard. If you want to accurately measure that switchboard, you need to be pretty well right up against it, in which case you might as well use a thermocouple. Another thing to bear in mind, of course, is that if you're measuring the switchboard and it's 3 meters away, you're not only measuring the temperature of the switchboard, you're also measuring the temperature of all of the air in between. And if that air warms up and cools down, it's going to change the reading. So once again, you need to get as close as you possibly can to the target to eliminate the fact that there's air in between. So if you're using infrared pyrometers, you need to get as close as you can to the target. You need to adjust the emissivity. The best thing to do, the best option, is to have an object and paint the object black. Then you know your emissivity is going to be around about 0.95, and be as close as you possibly can to that object. Here's a typical temperature sensor, infrared temperature sensor, handheld one. And here you can see the thermocouple plugged into it for calibration. So that's the thermocouple that we would use for recalibrating it, for establishing the emissivity. And emissivity has a symbol, that's the emissivity. Okay, so there's a good temperature sensor. Now, where people get confused, where people get mixed up, is with the fact that these things also send out a tiny little laser dot. And if they send out a tiny little laser dot, people are mistaken into thinking that where that little laser dot is touching is what they're measuring. If you're a long distance away, you're also measuring the air in between. If you're a long distance away, the actual sensor is not seeing a tiny little dot. The sensor spreads out. And if you're not measuring something that's black, your emissivity is probably not 0.9. If you're measuring something shiny, then your emissivity is wrong. If you don't have a thermocouple, then what you do is, let me see, what do you do? then what you would do, I guess, is take the temperature of the device that you want to measure using some other type of temperature measuring thing, maybe even a bulb thermometer, and from that calculate how far out your infrared sensor is and adjust the emissivity in your infrared sensor until it reads correctly. So you point the thing at the object you want to measure. If the thermometer is reading, say, 50 degrees C, and your infrared sensor is reading 30 degrees C, then you adjust your emissivity until both of them agree. And then your infrared gun is calibrated for measuring that particular object, and only that particular object.